Welcome to Lecture 8, where we will be studying depth images and point clouds. As we've noticed before, 3D information is critical for robots when it comes to navigation and manipulation. 2D cameras, as we saw last time, can provide 3D information, but it needs some a priori assumptions. It would be better if our sensors can provide unambiguous data. So in this chapter, we're going to study 3 ways in which we can get that 3D information from sensors using, number 1, a tilting LiDAR, number 2, stereo cameras, and number 3, depth cameras. Let's start in section 7.1 using depth from scanning LiDAR. Here we're going to look at a gazebo plugin of type GPU laser. We're going to look at some of the settings and how to visualize it in RViz while extracting a Cartesian centroid. So LiDAR measurements often occur in polar coordinates, and they usually slice a single plane. If you use advanced LiDARs, actually you will have multiple laser sources. This is common in autonomous cars, and those LiDAR sensors might be tilted at different angles, so the plane or the slice is getting a different cut of the world. And then all of this can be converted into 3D data in spherical coordinates. Now, there's a way that we can take one simple LiDAR and then get 3D information from it. How do we do it? We need to use a spinning mirror. So it's a mirror that is going like a clock, just rotating, and we can do that by placing it on a revolute joint. So, for example, if you look at the video here on the right, this was a simulation on gazebo of the Atlas humanoid robot sitting down in the front seat of a car. And here the robot is visualizing what is the steering wheel. And as you see, as I play this video, there is a pass of the sensor across this plane of the steering wheel. And with each pass, we can get a more complete picture of the environment in front of us, as long as we hold those point clouds constant and not let them disappear. So you can see that after a number of passes, the steering wheel here is very, very clear, and then this can be very useful for us to know where exactly that steering wheel is and how to grasp it and so forth and so on. You can find links to this video both on YouTube and Yoku right here. This spinning LiDAR was built into what is called the Carnegie Robotics Multi-Sense Head. You can click here for more information. So we know that the LiDAR now is on a revolute joint. But also pay attention that joint often will have limits, and that this joint will basically be oscillating or wobbling back and forth. Here is another example of the PR2 robot using a spinning LiDAR. Okay, well, let's start by looking at the URDF file for this LiDAR and see how it's represented in gazebo. Let's open a terminal right here, and we're going to be working from the package LiDAR Wobbler. So we can use raw set. Like this. So at the top, we're building all of our links and all of our joints. Here we're going to have a movable link on top of which we're going to add the simulated LiDAR and have all the visual, collision, inertial properties, and physics simulation. So this is going to be called a LiDAR link right here. Then we're going to have joint 1, which in this case is no longer fixed but revolute, and so that has the parent as link 1 and the child as LiDAR link. You can see here that we have some, well, in this case it's 365 degrees, or 0 to 6.28 radians, or 2 pi radians. So here we can do a full revolution. And finally we get here to the Gazebo plugin to simulate the LiDAR sensor. So here we're going to say, hey, this is going to be a type of GPU ray, and we're going to call this SICK LiDAR sensor. SICK is a popular company that produces LiDARs, so we're using this name here. There's no further change in pose from where we have it on the link. This is going to have an update rate of 40 Hertz for our data. And let's see how that LiDAR can scan. It'll move from negative 1.57 radians to positive 1.57 radians, or negative 90 to plus 90. And the resolution is going to be every 1 degree. Okay, so basically here we're going to get about 181 samples going from left to right. The range, or how far the rays can perceive data, is at a minimum 0.10 meters or 10 centimeters, and maximum of 80 meters with a resolution of 1 centimeter. For noise, we're going to have a small Gaussian noise, zero mean, and a standard deviation of 0.01, just to introduce some variability into the sensor and simulation. Finally, we get to the plugin, and so here, this is the key. The file name that we're going to use is libgazebo ROS GPU laser. Okay. Here you can provide any name you wish. We're going to use Gazebo ROS LiDAR controller, and all the data is going to be published to this topic, scan, and here we will use the frame LiDAR link for our LiDAR sensor. Okay, these frames you can visualizing by running run TF view echo as well. Okay, so we know the plugin is the GPU laser plugin. We're going to call this a GPU ray sensor, and we're going to have a namespace LiDAR wobbler. We know joint 1 is going to go from, in terms of limits, 0 to 2 pi, and this joint is controlled by the ROS control plugin, and as we have seen many times before now, we will need some parameters for the controller of this joint. So we're using the YAML file for 1 degree of freedom control parameters, which will be launched or started in a launch file later. So now that we have our LiDAR, the next thing we want to do is be able to control how it's going to move. So in this example that we're going to introduce next, we're going to have a wobbling joint, a joint that moves kind of like according to a sine curve. We'll look at the code in a second, wobbler sine commander.cpp, but just to get an overview of the code, we're going to start by setting joint limits and the starting joint values. Then we're going to ask a user to tell us a frequency and an amplitude that we will use for our sine curve generation. And within this while loop, we're going to iteratively compute a phase value for the sine curve, and then generate a joint angle from that function, publish it to the simulator, and then move the joint angle for the sensor to also be moved along with it. So let's open the wobbler sine commander, same package. Okay, since we're going to be publishing joint state information for a single joint, oh here, sorry, we're not going to use this one right here, just standard messages float 64. Here's our joint command limits. We're going from, these are globals and constants that are not going to be able to be changed. And we go almost to 3.1452, which is pi. And in main, we initialize our node. As signed commander, we create our node handle and our publisher object, where we're going to publish the position command. This is going to be standard messages float 64. And here we're using this long topic, LIDAR wobbler joint 1 position controller command. Okay, so then we have these starting numbers for the position. The joint angle will be Q command equal to 0, and the amplitude will start at 1.57. We'll create variables for the frequency, the omega variable, and a mid-range joint angle. So this mid-range is just Qmax plus Qmin divided by 2. Okay, so here now we can start to ask the user for amplitude, which is saved right here, and then for frequency, which is saved right here. The frequency information can be used to compute omega. So omega is equal to 2 pi f, which is this equation right here. And then we're going to be updating the phase using this information. So we set that new variable to 0, and we're going to sample at a rate of 100 hertz. So the Ross rate class can help us to create an object that's going to be set equal to 100 hertz, 1 over dt. And then we're going to come in here into the while loop. So as long as the node is okay, then that phase is the addition of phase plus omega times dt, or omega t. Okay. We do a little check. If our phase is greater than 2 pi, then we're going to turn that to the negative value and just flip over. Here, the final equation for the joint angle command is the amplitude times the sine of the phase. And this Q mid is just an offset that helps us to start at a good range. You know, this is just a healthy value to start off at. Once we have Q command, we are going to set it equal to our Ross float 64 type dot data, that element of the structure, and then we're going to be ready to publish right here, and also have the sleep call on our Ross rate object. So let's see how this runs, and let's, number one, get Gazebo started, and then we're going to do the LIDAR wobbler launch. This launch file, I'll show it to you in a second, can load the controller configuration parameters, load the URDF, spawn the object or the LIDAR into Gazebo, and then start the controller plugins using a spawner from the controller manager. Finally, we do also start the robot state publisher and the joint state publisher. So let's come over here. We can start Gazebo first. Do this. Okay. Now let me show you that launch file right quick. So here we have the LIDAR wobbler.launch. Make that a full screen. So you can see here that on Ross param, we get this file, 1 degree of freedom controls YAML file, and then we load it. And then, so Ross param, remember, is associated with files. In contrast, parameters, like a single parameter, will use the param tag. We set the name to robot description, and then just simply load the URDF file right here. To spawn the robot into Gazebo, we use Gazebo Ross spawn model node, and on the arguments, we're going to say the parameter name is robot description. We're using a URDF type file, and we're going to load a model with the name LIDAR Wobbler. That's how it knows. The next part is the controller, starting up the controller plugins using the controller manager. So this is part of the package controller manager. The node is spawner, and then we're going to use this namespace LIDAR Wobbler, and the arguments is going to be the controllers we want to use, which are defined in this YAML file, right? So we have joint state controller and joint one position controller. Then we have these two nodes that we want to start, the robot state publisher. So package and node share the same name, and we can do a remapping from joint states to LIDAR Wobbler joint state, so we keep the same namespace right here. Joint state publisher is basically the same package, same type, and same remapping. So once we do that, we should start to see our sensor right here. Okay, so we have simulated this LIDAR as a simple block. So we want to test the LIDAR, and right now we have an empty world, so it's not very useful. We could insert the starting pen and a beer around it, and then look at the sensor data using our viz. When we do our viz, we can set the fixed frame to world and also modify the settings for the laser scan display to make the data decay a little bit slower. So let's go back to Gazebo, maximize the screen. Let me zoom out a little bit so it's easier to insert the starting pen. So we might have something like this. And we might also insert a beer bottle. Somewhere like so. Okay, so if we want to then visualize the data, it would be useful to start RViz. So I can open a new terminal, maximize the screen, and then open RViz like this. So our fixed frame is already set to world. Okay. We have our robot model that we need to turn on. And we can add a laser scan right here. Adjust the topic. Maybe use points. Change the intensity to an axis color, like so. And then the decay time to 10. We can also change this axis information to something like this, like Y. And over here on Gazebo, we could potentially make this object bigger by using this scaling tool. Sorry, it seems like I'm stuck. There we go, using the shift key. So that also shows up right here in RViz. Okay, we're still not moving our LIDAR, but we are currently visualizing that information right here. So now if we want to move our LIDAR, we can activate our node, wobbler sign commander, and display that information here as well. So let me maybe split this window. So here we're going to enter an amplitude, enter a frequency. Let's do 10. Here's gazebo. So you can see in a second how that sensor is going to wobble. And here the decay time also plays a role. Let me run also other settings. For example, let's change the amplitude to 1 and then just have a frequency of 1 hertz. Here you can see what looks more like this limited sine wave going back and forth. And because we have a decay time set equal to 10, basically we're seeing that range right there. If we change this to 1 second, or 0.5 seconds even, you can see that our data points are created but then disappear very quickly. When this number is changed to a larger number, like 1 second even, the points seem to be pretty consistent. Okay, if we run this again and maybe do 1.57 radians and still keep a 1 hertz frequency and change the decay time to 0.5, you're still going to see the same phenomena, but just at a wider amplitude. Okay, so it depends. This is just useful for visualization, but normally your decay time might be a higher value to help you actually look at what's inside the environment. But this is always very, very fun to be able to see the data visualized in RViz from a LiDAR. And remember here, the visualization, we're choosing an axis color transformer. So this is saying that here is probably a negative y-axis, a positive y-axis, and as the location along the y-axis is changing, so is the color. If you change this to the x-axis, then we're getting this kind of transformation. All of these points are the same color because they're along the same x-axis. And as you move along the x-axis, you'll get a transformation of color. And then here for the z-axis, it's same changes because the z-axis is changing slightly for the points as they move along the x direction. Okay, so let me go back to our presentation. And so you can see here that the LiDAR points which originate in polar coordinates are also represented in terms of Cartesian coordinates and the world frame. There's some interesting things that we can do with RViz. There is an icon at the top bar where you can see a plus sign. This is a place where we can insert tool types, and there is one specific tool called Publish Selected Points. Now this plugin, this tool type is a plugin, and it's available through the code in our book. What this is going to allow us to do is use our mouse button to select a series of points in the point cloud and then publish the centroid and along with a little bit of other information to a topic called selected points. Let's see. Now here the type of our topic is going to be sensor messages point cloud 2. I included this link for ROS PCL data types here for you to see the difference between point cloud and point cloud 2 messages. Now the node takes those point clouds and then publishes the XYZ coordinates of the blob centroid. So when all the points that I selected, I'm going to compute a centroid and return the XYZ coordinates. If I want to use this specialized node, I'll need to run the following command, run PCL utilities compute selected points centroid. And so here is, can we make sense of the result? So let's take a look. I'm over here. I should open RVis one more time. Go into my panels and displays. Not view, sorry. Sorry, I took that away a moment ago. Okay, we have that, our fixed frame here, world, so that's correct. I can also close this. And here in my tool type, I can add publish selected points. Let's set the style to points as well. And maybe their size to 5, and maybe a decay time 0.5. Okay, so we have this visualization right here. Go back to the terminal. Let's run this. Maybe at 3.1452 and maybe 10 Hertz. Now this is being heard by the joint limits. Let me set that maybe to 3 and then to 10. So we're getting this kind of visualization right here. Getting stuck there again. Actually, let's do what we were doing before. And this time, change the decay time to 1. So in this very simple example, I can then come over here and click Publish Selected Points. And this will allow me to select a range of points in a point cloud. Those will turn into bluish color, which might be hard to see here, until they decay. Now let's open a new window. I could say Ross topic echo selected points. Now nothing is going to happen here because I'm not yet publishing anything. It only happens when my tool type actually selects a blob. So as soon as I do that, here comes all the data from the point cloud points. That's the data and a little bit of other kind of information, including height and width. So this data topic, so this topic data is then going to be used by this node from PCL utils, compute selected points centroid. So here the node is waiting for a patch of points, which again I can just select right here. And as soon as I do that, it'll tell me that I've received a new patch. It'll tell me the dimension, 118 by 1, the frame ID, and finally the centroid of the selected points. So here it's saying the X position of the centroid is at 0.03. So for example, this ray or this line right here is right now representing the y-axis. So the x-axis is the change from the middle of the camera to here. So it's a small change. It says that along the y-axis we're at 0.85 meters. So let me maybe rotate here, or let me do a new patch. So if I do this one here, right now it's at 0.21, and it's saying the height is almost 0.01 centimeters. So that's how we make sense of the results. Let's do another patch over here. We get a negative 0.53 in the y direction, 0 in the z, 0 in the x. If I choose something along here, the edge, that x value changes to 0.12, and the y is close to 0, the z is close to 0. If I choose something on the other edge, I get a change in x's. The y is almost 0 and the z is almost 0. So this is how the tool type and the node can work together to provide us some useful information about the environment.